What if I told you some machines simply refuse to die? Built more than a century ago, they still move, glow, chime to life, outlasting empires, wars, and even the people who invented them. Many were abandoned, rediscovered, restored, and still work exactly as they did a century ago. Here are 15 creations that should have stopped working a lifetime ago, but didn't.
Number 15. The Newcomen engine at Dartmouth. The Newcomen engine at Dartmouth was completed in the year 1725. It is one of the oldest machines on Earth that can still move in the same way it did when the Industrial Revolution began. What makes it so shocking is how much power it created with parts that look simple by today's standards. It was designed by Thomas Newcomen at a time when people had no advanced tools, no electricity, and no modern factories. Yet the engine could perform work that entire teams of workers could not do on their own. The machine solved a major problem in mining. Deep mines constantly flooded with water, and there was no reliable way to remove that water once miners dug past a certain depth. The Newcomen engine changed everything by creating a system that used steam and air pressure in a very surprising way. Steam was pushed into a tall metal cylinder and filled the space around a piston. Cold water was then sprayed inside the cylinder. The sudden cooling caused the steam to collapse, and that collapse created a powerful vacuum. The vacuum pulled the piston downward with enough force to lift heavy pump rods inside the mine. The large wooden beam connected to the piston rocked up and down, and this motion drove the pumps that cleared the mine of water. This system allowed miners to dig deeper than anyone had ever imagined. Entire mining regions became more profitable because the machine worked day and night without tiring. It did not need brakes, and it did not get weaker with use. It kept removing water as long as there was fuel to heat the boiler. Many machines from the 1700s broke down or disappeared, yet this one continued to operate because its structure was strong and its design was reliable. The Dartmouth engine still has its original beam, boiler shell, cylinder structure, and many of the same valves that were used nearly 300 years ago. This is extremely rare because thousands of new engines once existed and almost all were destroyed when newer steam engines replaced them. The Dartmouth example survived only because people decided to preserve it instead of throwing it away. Its survival means that visitors can see a real piece of early industrial engineering instead of a replica. The machine once worked at a mining site and performed non-stop pumping operations for many years. Today, it is located at the Dartmouth Visitor Center in Devon in England. It has been restored with a gentle, modern system that moves the piston and the beam very slowly. This prevents the historic metal parts from being damaged while still showing exactly how the engine worked when it was at full power in the 1700s. The Newcomen engine at Dartmouth is not just an old machine. It is a fully functioning survivor from the beginning of the industrial age. It gives visitors a direct view of the technology that shaped modern machinery, and it proves that early engineers created systems that were far more durable than most people realize. Number 14. The Solar Railway and its electric locomotives. The Solar Railway in Mallorca has been operating since the year 1912, and it still runs with the same electric locomotives, track layout, and power systems that were installed more than 100 years ago. The railway stretches for about 27 kilometers between the city of Palma and the town of Soler. The route runs through steep mountains and deep valleys, and it once served as the main way for farmers to transport oranges and olives to major markets. Construction began in the year 1907. Workers had very limited tools and relied on hand drilling, dynamite blasting, and stonemasonry. It took 5 years to cut 13 tunnels, build bridges, and carve a safe path through rock walls that rise sharply on both sides of the track. When the line opened in 1914, it became one of the earliest fully electric railways in Europe, which was an extraordinary achievement at that time. The locomotives use 4 separate traction motors. Power is controlled by a simple hand-operated system that regulates the strength of the electric current through a set of resistors. The braking system is fully mechanical. Although the locomotives are not fast, they climb steep slopes with no difficulty. They can pull carriages through the 2,800-meter solar tunnel, which is one of the longest hand-carved railway tunnels still used today. Many early tunnels have been rebuilt or replaced with modern versions, but this one still carries trains through the same stone walls workers cut by hand before the First World War. The solar railway kept operating during the Spanish Civil War and during both World Wars. When engineers inspected the system in the 1980s, they were shocked to find that many of the original generators, transformers, and switching devices were still functioning. The equipment required cleaning and adjustment, but the basic parts were strong enough to keep going. The locomotives do not depend on fragile electronic components. Everything can be repaired with basic tools. The workshops still use the original early 20th century blueprints to create replacement parts. Number 13. The Centennial Light Bulb. The Centennial Light in Livermore, California is one of the most unbelievable machines ever created because it has been turned on since the year 1901, and it has almost never stopped working. Modern light bulbs often last a few months or a few years. This one has been glowing for more than 120 years. It is a carbon filament bulb made by Shelby Electric in Ohio during the late 1890s. The company used hand-blown glass and extremely thick carbon filaments. These materials were far stronger than the thin metal filaments used in most modern bulbs. The Centennial light also runs at a very low temperature, which prevents the filament from burning out. The original vacuum inside the bulb is still intact. This vacuum keeps air away from the filament and slows down the chemical reactions that normally destroy bulbs. The Centennial light only uses about 4 watts of power and gives off a soft amber glow. It is not bright, but it is incredibly stable. Its slow and gentle operation helps explain its extraordinary lifespan. The bulb was first installed in the Livermore Fire Department on L Street. Since then, it has almost never been switched off. The few interruptions came from building maintenance or temporary power failures. When the fire department moved to a new station in the year 1976, the bulb was kept connected to power the entire time, so it would not lose its continuous operating record. In the year 2015, a digital monitor confirmed that the bulb had passed 1 million hours of total illumination. Engineers continue to study this bulb because it helps them understand how careful manufacturing, strong materials, low temperatures, and stable electrical conditions can dramatically extend the life of a machine. It remains an active example of how early electrical engineering sometimes achieved results that modern technology still struggles to match. Number 12. The Zettler Electric Clock. The Zettler electric clock inside St. Michael's Church in Munich is one of the most incredible timekeeping machines still running today since the late 1880s. This clock has survived more than a century of daily use with almost no major repairs. It was built by Johann Baptist Zettler during the very early days of electrical engineering. He combined traditional pendulum mechanics with a small electrical system that supplied just enough energy to keep the pendulum moving. The clock works in a surprisingly simple way. A standard pendulum swings back and forth. A low-powered electromagnetic coil gives the pendulum a tiny push at the right moment. This push replaces the heavy gear trains that older tower clocks relied on. Fewer gears mean less friction. Less friction means less wear. The result is a machine that stays accurate within a few seconds each week, even though it was designed before the invention of modern precision tools. The materials used in this clock are another shocking reason for its long life. Zettler installed platinum contact points that do not corrode. He used brass bearings that remain smooth even after millions of movements. The pendulum sits inside a wooden frame that protects it from vibrations and temperature changes. Records show that the clock has only needed cleaning, lubrication, and occasional rewiring since the early 20th century. None of the main parts have ever needed replacement. The clock has been in the same church since it was installed. It survived bombings during both world wars. It survived building repairs. It survived complete changes in caretakers. Through all of this, it never stopped running. The design became a foundation for later electric clocks used in schools, train stations, government buildings, and large public networks. Researchers still study Zettler's work because it shows how a very small amount of electrical power can keep a mechanical system moving for more than 100 years. Number 11. The Ffestiniog Railway Steam Locomotives. The Ffestiniog Railway in Wales operates some of the oldest working steam locomotives in the world. Two of its most significant engines, Prince, built in 1863, and Palmerston, built in 1864, have remained in service for more than 150 years. They represent rare surviving examples of early narrow-gauge locomotive engineering that still perform regular duties. Both locomotives were constructed by George England and Company, a London firm known for compact locomotive designs suited to steep gradients and tight curves. Prince and Palmerston are small, four-wheeled tank engines with simple two-cylinder layouts, low centers of gravity, and short wheelbases. These features made them ideal for hauling slate trains through the rugged terrain of the North Wales quarries. The locomotives use saturated steam generated by small boilers with power delivered through external valve gear to driving wheels designed for steady traction on narrow-gauge rails. Their design emphasized mechanical simplicity, reliability, and ease of maintenance, which is why they remain operable after more than a century of service. During the 19th and early 20th centuries, both engines hauled slate, workers, and supplies along the Ffestiniog line under demanding industrial conditions. When diesel traction began replacing steam, the locomotives were preserved rather than scrapped, becoming part of the emerging heritage railway movement. Mid-20th century overhauls replaced consumable parts such as boiler plates, tubes, and bearings while retaining original frames, castings, and running gear. This allowed the locomotives to return to service for heritage operations, exhibitions, and seasonal passenger trains. Their continuous life on the same railway has preserved their historical authenticity. Today, Prince and Palmerston remain operational at the Ffestiniog and Welsh Highland Railways, maintained by engineers at Boston Lodge Works, one of the world's oldest working railway workshops. Their preservation has advanced modern steam engineering through improved boiler fabrication, non-destructive testing of historic castings, and custom machining for obsolete components. More than 150 years after construction, these locomotives still run through the Welsh mountains, demonstrating the resilience of early British steam engineering. Number 10. The San Francisco Cable Car Powerhouse Machinery. The San Francisco cable car system is one of the oldest continuously operating mechanical transportation systems in the world. At its center is the powerhouse machinery, first installed in the year 1873, which still follows the same mechanical principles that powered the network in the 19th century. This makes it a rare example of large-scale urban infrastructure that continues to function in its original form. The system relies on continuously moving steel cables running beneath the streets through narrow underground channels. Inside the powerhouse, large electric motors drive massive winding drums, each dedicated to a specific cable route. The cables run at a constant speed of roughly 9 miles per hour, and each cable car grips or releases the moving cable using a mechanical clamp. This simple mechanism allows the cars to accelerate, climb steep hills, and stop with precise control. The machinery includes heavy steel drums, reduction gears, tensioning devices, and bearings housed at the Washington and Mason powerhouse. Although the original steam engines were replaced with electric motors, the core mechanical layout remains faithful to the 19th century design. Earthquakes, fires, and modernization efforts threatened the system over time, yet the city repeatedly chose preservation, reconstructing the equipment to match original specifications. Major rebuilding in the early 1980s involved fabricating new components using modern methods, but the mechanical architecture stayed true to its historic blueprint. The machinery has always occupied the same powerhouse, supported by preserved diagrams, castings, and structural plans that guide every restoration. Today, the powerhouse serves as both the operational center of the cable network and the San Francisco Cable Car Museum. Visitors can watch the winding drums in motion and see how tension, speed, and load are managed across the system. Number 9. The James Watt Beam Engine. At the London Museum of Water and Steam stands one of the oldest working steam engines in existence, an 1812 beam engine built using principles pioneered by James Watt. First installed at a canal pumping station in Scotland before later being moved to Kew, the engine remains fully functional more than 2 centuries after its construction. The machine operates with a massive overhead beam nearly 10 meters long, rocking back and forth as it transfers power from a vertical piston to a rotating flywheel. This flywheel once drove pumps that supplied clean water to London. Steam expanded inside the engine's 44-inch cylinder, producing steady, reliable strokes capable of lifting thousands of gallons of water each hour. The engine was designed for continuous operation with minimal maintenance, a goal it achieved for almost a century. When retired from daily service in the early 20th century, engineers found the mechanism in remarkable condition. It was later restored using low-pressure steam for museum demonstrations, allowing the engine to operate safely while preserving its original 19th-century cast-iron components. Every valve, bearing, and linkage still functions according to its historical design and is manually oiled and adjusted during operation. During special demonstration events, museum engineers start the engine so visitors can witness the same rhythmic motion that once powered essential infrastructure across Britain. The original beam still carries visible foundry marks from 1812, and the iron castings remain structurally sound after 200 years. The James Watt beam engine at Kew is more than a preserved artifact. It is a living example of early industrial engineering, demonstrating the durability of steam-powered machinery and the craftsmanship that helped drive the modern world. Number 8. The Laxey Wheel. The Laxey Wheel on the Isle of Man, completed in the year 1854, is one of the largest working water wheels in the world and one of the oldest mechanical structures still operating in its original location. Built to pump water from the Great Laxey Mine, it stands 72.5 feet in diameter and 6 feet wide. Designed by engineer Robert Casement and named after Lady Isabella Hope, the wheel uses a gravity-powered system that requires no coal, steam, or external fuel. Water fills a series of buckets along the outer rim, creating a weight imbalance that turns the wheel. This rotation drives an extended system of rods and cranks stretching more than 600 meters underground to operate drainage pumps. The design provided the mine with a cost-effective and reliable method for clearing water from deep levels during the Victorian era. The wheel served the Great Laxey Mine for decades until mining ceased in the year 1929. Instead of being dismantled, it was preserved as a historic landmark. Major restorations in the year 1989 and the year 2022 reinforced timber supports, replaced deteriorated ironwork, and improved protection against weather exposure. Despite this work, much of the original gearing, crank assemblies, and bearings remain intact, and engineers confirm that the wheel still operates according to its 19th-century mechanical principles. The wheel has never been moved and continues to overlook the Laxey Valley from its original hillside setting. Today, it turns during the tourist season using the same gravity-fed water channels that powered it more than 160 years ago. MK's national heritage maintains the structure, allowing visitors to observe the rhythmic motion of the mechanism and climb to the upper viewing platform. The Laxey wheel has also inspired modern research into sustainable mechanical power. Data from its long service has informed low-impact water-driven generators and gravity-based pumping systems for remote and rural applications. Modern conservation tools, including moisture sensors and stress analysis, were applied during its latest restoration. Number 7. The Zexia machine and fabric printing press. In a workshop in Leipzig, Germany, an original Zexia machine and fabric letterpress built in the year 1910 continues to operate more than 1 century after its manufacture. Leipzig, once the printing capital of Europe, was known for its advanced pressmaking industry, and this machine stands as a surviving example of the region's early 20th century craftsmanship. Designed and produced in cabinets by a respected Saxon engineering firm, the press still prints with its original cast-iron frame, rollers, and mechanical plates. The press is manually fed and belt-driven using a flywheel and crankshaft to generate smooth, rhythmic motion. It can run with a foot pedal or a small electric motor. Sheets of paper are pressed against metal type or etched plates, while a precisely aligned inking system coats the rollers evenly. Despite its age, the press maintains remarkably tight tolerances, reflecting the precision of German industrial engineering at the time. During operation, every part of the mechanism remains visible. Gears turn steadily, cams lift and fall, and rollers apply ink with uniform pressure. The solid cast-iron structure resists vibration, contributing to consistent print quality over decades of use. The press began its life in a commercial print shop, operating continuously until the year 1963. When the shop closed, a master printer preserved the machine and kept it functional. It operated intermittently during the Cold War, but returned to regular use in the 1990s when it was relocated to its current Leipzig workshop. Aside from consumable parts like rubber rollers, the machine retains its original components. Today, the press is used for demonstrations, fine art editions, small print runs, and educational work. Craftspeople maintain it through routine oiling, cleaning, and belt adjustment. Its survival has inspired renewed interest in traditional letterpress methods and has informed the development of hybrid systems that combine digital design with mechanical impression. Number 6. The Tower Bridge hydraulic system. When Tower Bridge opened in London in the year 1894, it represented one of the most advanced engineering achievements of the Victorian era. The bridge combined suspension elements with a bascule mechanism that allowed the central roadway to lift for passing ships. This motion was powered by a steam-driven hydraulic system, parts of which remain functional today, making it one of the oldest continuously operating mechanical infrastructures in the world. The original system used steam-powered pumping engines to pressurize water, storing this energy in large hydraulic accumulators inside the bridge towers. When a vessel required passage, valves released the stored pressure through a network of pipes, driving heavy hydraulic pistons that raised the bascules, each weighing more than 1,000 tons in about 1 minute. Slow-moving cast-iron gears, large flywheels, and oil-lubricated bearings ensured smooth, reliable operation and minimized mechanical wear. For nearly 80 years, the bridge relied entirely on steam power. In the early 1970s, the system was upgraded to electro-hydraulic equipment using electric motors and modern pumps. However, engineers preserved the original steam engines, accumulators, and control valves in their original locations. Although they no longer lift the bridge daily, they remain fully operational for demonstrations, with many components dating directly to the 1890s. The machinery survived 2 world wars, structural renovations, and changes in river traffic without relocation. Today, visitors can tour the Tower Bridge engine rooms, where the preserved steam engines and flywheels are maintained in working order by specialist engineers who keep the components lubricated and aligned for test runs. The preserved system has influenced research into mechanical durability, stress monitoring, and low-energy hydraulic storage. Modern engineers study the 19th century accumulator design for use in remote lifting systems and flood control structures. More than 130 years after its completion, Tower Bridge still raises its bascules hundreds of times each year, following the same mechanical principles established in 1894, and stands as a rare functioning monument of Victorian engineering. Number 4. The Poughkeepsie Ice Machinery Plant Steam Pump. On the banks of the Hudson River in Poughkeepsie, New York, a 19th century steam pump continues to defy expectations of mechanical longevity. Built in the year 1873 by the Worthington Pump and Machinery Corporation, this massive duplex steam pump was installed at the old Poughkeepsie Ice Machinery Plant and has operated in one form or another for more than 150 years. Worthington was a leading innovator in high-pressure pumping systems and supplied equipment for New York City's earliest waterworks. At the time, ice production was transitioning from natural harvesting to mechanical manufacturing, and factories required a constant supply of cold water to feed compressors and condensers. The Poughkeepsie plant relied on Worthington's direct-acting duplex design, which used 2 steam cylinders and 2 water cylinders working in synchronized opposition. Each piston stroke powered the next, eliminating the need for a crankshaft or flywheel and reducing mechanical wear. This balanced action is one reason the pump has endured for so long. Worthington engineers designed the machine for generational service with tightly balanced pistons, corrosion-resistant cylinder linings, and a 20-ton cast iron frame that absorbs vibration and allows near-silent operation. When the plant closed in the mid-20th century, preservationists ensured the pump survived. After minor repairs and connection to a low-pressure boiler, it ran almost immediately as if no time had passed. Today, volunteers operate it a few times each year under the Hudson River Maritime Museum, giving visitors a rare experience of living 19th century steam engineering. Number 3. The H. Heidelberg Original Printing Press. The H. Heidelberg Original Printing Press, introduced in the year 1914 by H. Heidelberger Druckmaschine and AG, became one of the most influential and enduring printing machines ever produced. Nicknamed the windmill for its rotating paper gripper, the press reshaped small-scale commercial printing. More than 1 century later, thousands of units still operate worldwide, many of them in daily professional use. The windmill's defining feature is its rotating arm, which swings in a circular motion to pick up individual sheets of paper. This arm synchronizes precisely with the platen's opening and closing, ensuring each sheet receives uniform pressure. Early models achieved more than 4,000 impressions per hour, an impressive speed for the early 20th century. Throughout the 20th century, the H. Heidelberg windmill became a standard fixture in print shops across Europe, North America, and Asia. It produced business cards, letterheads, labels, packaging, and countless commercial products. Many presses survived both world wars, often outlasting the companies that originally purchased them. In some workshops, a single press has served 3 or 4 generations of printers. Even as offset and digital printing gained dominance, windmills remained essential for tasks requiring strong, consistent pressure, such as embossing, foil stamping, and die cutting. Their reliability, low maintenance needs, and versatility kept them in service worldwide. The windmill has influenced modern mechanical and printing design, inspiring improvements in paper handling systems, die-cutting equipment, and hybrid workflows that combine digital plate production with traditional mechanical impression. Some presses have exceeded 80 million impressions without major component replacement. Number 2. The Harwell Decatron Computer. Inside the National Museum of Computing at Bletchley Park stands one of the most remarkable survivors of early digital technology, the Harwell Decatron Computer, nicknamed the Witch. Built in the year 1951, it is officially recognized by Guinness World Records as the oldest working digital computer. More than 70 years after its creation, the machine still operates exactly as it did in its earliest days. The computer is an electromechanical system built with thousands of relays, vacuum tubes, and 828 Decatron gas-filled counting tubes that display numerical positions as glowing orange points. When running, the machine flickers with rhythmic light, each pulse marking a calculation. Unlike modern processors, the Witch performs operations at a deliberate pace of roughly 1 addition per second, allowing observers to follow each computational step in real time. Data is stored on punched paper tape, and relay switches perform the system's logic functions. The machine served scientists at Harwell until 1957, after which it was transferred to Wolverhampton and Staffordshire Technical College as a teaching tool. It remained in use until the early 1970s, then was placed in storage. Decades later, engineers undertook a meticulous restoration using the original circuit diagrams. In the year 2012, the computer was fully operational again without altering its logic or memory systems. Only wiring insulation was replaced for safety. Today, visitors can watch the Witch computer, its relays clicking and its decatrons glowing in spiraling patterns. Unlike most early computers preserved as inactive museum pieces, this machine still processes data in real time. Number 1. The Voyager spacecraft. Voyager 1 and Voyager 2, launched by NASA in the year 1977, remain the most enduring spacecraft ever built. Operating more than 15 billion miles from Earth, they continue to transmit faint radio signals nearly 50 years after launch. Despite being designed for a mission of only 5 years, they are the first and only human-made machines to travel beyond the Sun's magnetic boundary into true interstellar space. Each spacecraft carries scientific instruments, including magnetometers, plasma sensors, cosmic ray detectors, and 3 onboard computers. A 3.7-meter dish antenna provides communication, and a radioisotope thermoelectric generator supplies electrical power. At launch, each RTG produced about 470 watts of electricity, though the output steadily declined due to natural radioactive decay. Voyager 1 returned the first detailed images of Jupiter's storms and Saturn's rings before completing its primary mission in 1980. Voyager 2 became the only spacecraft to visit Uranus and Neptune. In the year 1990, Voyager 1 captured the famous pale blue dot image at the request of Carl Sagan, showing Earth as a tiny point suspended in sunlight. Soon after, to conserve power, their cameras were shut down, but their other instruments continued to operate. Voyager 1 entered interstellar space in the year 2012, followed by Voyager 2 in the year 2018. Their radio signals, weaker than a refrigerator light bulb, take more than 22 hours to reach Earth and are detected by giant 70-meter antennas of NASA's Deep Space Network. Communication is slow, at about 160 bits per second, yet sufficient for scientific data returned from beyond the planets. Engineers continue to upload carefully planned commands, adjusting power use and antenna angles with great precision. Although declining electrical output will likely end scientific operations around the year 2030, the spacecraft will continue silently through interstellar space for millennia. These machines have survived centuries, outlasting the people, industries, and eras that created them. They remind us that great engineering does not fade easily. Thanks for watching, and stay curious. There is always more to discover.